is going to be not mu naught epsilon, mu epsilon. Ah, dang it, I'm so used to writing it. Partial E respect to T. Now, that's similar to a vacuum, except for this one here, where we would have mu naught epsilon naught. Now we have mu and E. And we use that mu naught epsilon naught, we said, for a vacuum. The velocity of that electromagnetic wave is 1 over the square root mu naught epsilon naught. So in a linear material, which this material is a linear material, we said, the velocity of that wave is equal to 1 over the square root mu epsilon. Dang it. Just mu epsilon. So what we want to do, taking these two, what I'm going to say is, let's make the ratio of the velocity of the wave in a material over the velocity of the wave in a vacuum. And we're going to define that as N, and N, if you know from optics, is the index of refraction. And that ratio is going to be, we take the square roots. My apologies, I got these upside down. Velocity of the wave in a vacuum. Because N is greater than 1, and I should have realized for that to be greater than 1, this number's got to be smaller than that one. So this, and velocity in a material is always less than velocity outside of a material in a vacuum. This is of the wave in a material is going to be equal to 1 over mu epsilon over mu naught epsilon naught. Now, it says here, for most materials, mu is approximately equal to mu naught. So that's just 1. So this is really equal to index is really the square root of epsilon over epsilon naught. Basically, E sub r is that ratio of them. Okay? Really, it just depends on the permittivity, and epsilon, I'm pretty sure, is the permittivity of an object to free space. Okay? That permittivity ratio. Of course, the electric field, it makes sense because the electric field is what? How many times bigger did we say? What's it? 10 to the 16 times, I think, bigger. So, since it's so much bigger, then that's really what matters more. 10 to the 8th times bigger, I can't remember which. It's just much, 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 much bigger. The electric field vector is to the magnetic field vector. So the electric field, how things react to that electric field is much more important as it moves through to the electric field. They call this again, and it's E over E naught. E sub r is known as the dielectric constant. That's the dielectric constant, which for lots of things, you'll hear that term come up with. And by the way, this is greater than 1. Why is it got to be greater than 1? Because light travels much faster outside in a vacuum with nothing there than through a material. So index refraction is almost always greater than 1. Now, they go through here and talk about, now before I go on the rest of it, what's this index refraction tell us from optics? It's going to tell us how much that light is bent. It slows it down And if you go from one medium to another and you change speed, it will change direction. And by changing direction, it doesn't change frequency, but it actually does change the wavelength. You shorten the wavelength of it. And if you want to get an idea of saying, well, how do you know if you go from one material to another, it has to slow down? How do you know that? How does that make it change direction a little bit if it slows down some? You know that from driving, right? If you drive and you get off to the side of the road, you're like, oh, dude, I'm you're looking at your phone while you're driving. You're not supposed to, but you are. And all of a sudden you kind of swerve off, or you're listening, you're pushing the buttons on something on the phone because you're trying to do a playlist or something from Spotify on the radio, and then you're messing, something's going on, right? And you get off to the side of the road, you're like, oh, I'm going to go off in the ditch. You've got one set of tires on, one set of tires on the road. That's what they tell you to do. Just go over and swerve back on real quick. No, that's how you wreck. Because what happens is, as you go from the tires here in the grass to back onto the road, if you turn it fast, when you get back on the road, now you're in a material where it's going really slow, it's harder to make it go to going faster, it'll make that wheel turn that way even more. So if you do that real fast, you end up swerving, going into the other lane, bam, get head-on collision, or get sideswipe somebody, and get hurt somebody really bad. What do they tell you? If you're going off the edge of the road, slow down, and as you slow down, slowly, then get back on. And as you can feel a little tug on the wheel as you get on slowly. It'd be a whole lot more if you get on it really fast, and especially a whole lot more if you've got that wheel turned pretty sharp. Okay, that's an idea. Why does it make that sharp tug? Because it's changing velocities, going from one medium, the tire is, the dirt on the side of the road, to pavement. It's easier to go in pavement. That's like going from, inside a material to a vacuum. And actually it works in the exact same direction. Except one's a car tire velocity, and this is an electromagnetic wave. But it does change the direction of it. You've heard of Snell's law in optics, m1 sine theta 1 equals m2 sine theta 2. Most, even high school physics classes, if you had it, basic optics, that's pretty much, basic, one of the basic things they teach you about bending of light. That's used, and then you of course use that for your tracing light rays through lenses and stuff. Index refraction. The idea is just difference in a velocity of that wave. It's a function of those proportionality constants, which relate how well they let the electric and magnetic field, and in this case, for slowing things down, how well objects lets the electric field actually pass through it. Now, if you want to look at it at the microscopic level, it's oscillating, many times oscillating these atoms, oscillates them. They kind of absorb that radiation, oscillate, and then transmit, oscillate, transmit, absorb, oscillate, transmit. And that goes on down the path. That slows it down. Of course, the more objects you would have, it can change how much gets transmitted. Now, if I want to look at this, for the intensity of light in a material, well, now it's going to be where this is the velocity in the material of the electromagnetic wave in the material, and this is epsilon, the permittivity of the material. It really just changes the ratios. The concept is the same. The intensity is still a function of the electric field squared, but the magnitude will depend on how much it's slowed down and how much just lets it go through. They also talk about something about polarization. Really don't want to get into that right now because I really haven't talked about. These are basically polarization angles. What I will just say is at the boundary of the material, the electromagnetic wave polarized perpendicular to the surface versus parallel to the surface has different intensities. What I'm basically saying here is at the boundary, when light hits it, if light is, what are you doing, Chloe? Getting up there on my book bag? So at the here, Chloe, is that what you want? No, she wants on that book bag of mine. Okay. At that surface, if light comes in oscillating like this, a certain amount will be absorbed and go through. A certain amount will be reflected. That's this way. But if light's coming in polarized in this direction, a different amount will be absorbed and a different amount will be reflected. Polarized sunglasses on a lake work on this same effect. It absorbs light. Most of the light, when you see a reflection off a lake, it's polarized. Because most of the light that's reflected is coming in at this polarization angle, not this polarization angle. So if it's coming out in this polarization angle, you know that, I just have to make my polarizer cross it, and then you can absorb that intensity of light. So you don't see that reflection off the lake or off a car, which is what we call glare, or off even a road. You don't see that if it's way far out there. You only see it gets absorbed so you can see the road or down to the water better for fishing glasses. So polarization angle matters to be, if it's polarized in this case parallel or perpendicular to that surface, it will matter, it will change how much is actually transmitted into the material. Okay? And we're going to talk next time at normal incidence, how much gets reflected, electric field, B field. We'll get into that, and then we'll change it to off axis and talk a little bit more into that next time. Okay, and that's all I've got for the first two sections.